Hello everyone, thanks for coming. And today we are going to do a review of our week 5 lectures. So first, we talk about relation. Relation is defined for elements in a set A. So the relation is also a set. It consists of two element lists, which are also named as ordered pairs of objects. We say that X are Y if and only if the two element list XY is in R. Note that sequence matters. XY does not equal to YX. Suppose that R is a relation on A. There are few properties of the relation. R is reflexive provided that for all X in A, X are X. R is irreflexive provided that for all X in A, X and X does not in R. Note that irreflexive is not the converse of reflexive because a set can be both reflexive and irreflexive, which is the empty set, and neither reflexive nor irreflexive. R is symmetric provided that for all X, Y in A, X are Y implies Y are X. R is antisymmetric provided that X are Y and Y are X implies X equals to Y. So this is a case when we have the smaller or equal to. So if X is smaller or equal to Y, if Y is smaller or equal to X, then X equals to Y. R is transitive provided that X are Y and Y are Z imply X are Z. So this is like equals to or greater than, smaller than. We also have the inverse of a relation denoted by R inverse. So it's basically to change the sequence of X and Y into Y and X. Let R be a relation on set A. We say that R is an equivalence relation provided it is reflexive, symmetric, and transitive. So the trivial example would be the equal to sign. Also, in the same subset of A, this will also establish an equivalence relation. A more interesting example would be the congruence modular n. We say that X and Y are congruent modular n provided that n can divide X minus Y, so we can prove that it is also an equivalence relation. With the equivalence relation, we can define equivalence class. So here are some important properties of the equivalence classes. Equivalence classes are non-empty. So different equivalence classes are mutually disjoint, which means that they don't share a common element. The union of all equivalence classes are the whole set A. One way to get different equivalence classes is to have partitions of a set. A partition of A is a set of non-empty pairwise disjoint subsets of A whose union is A. There is a natural equivalent there in a partition can naturally give rise to different equivalence classes of A. So the relation is in the same subset as we can verify that this is indeed an equivalence relation. We learn binomial theorem to investigate how many equivalence classes, different equivalence classes we can get from a set. So the binomial theorem is let A be a non-negative integer, then x plus y to the power n is the summation of n choose k times x to the power n minus k times y to the power k. We also have the property that n choose k is equals to n choose n minus k because choosing k means we are leaving out n minus k elements. We also have the Pascal's triangle and Pascal's identity to get an induction formula for the binomial numbers. Thanks for listening.